we are very pleased to have Deeparnab here for the second talk in this monotonicity festival. So today we'll be telling us about isoperimetric theorems, part testers, and their analysis. Before we go into this, let me introduce Deeparnab again. So Deeparnab is an associate professor at Dartmouth College. Before this, he was at Microsoft Research Bangalore. He did his PhD at Georgia Tech, and he's interested in a bunch of things like relative combinatorial optimization, sublinear algorithms, and he has done foundational work in all of these areas. And thanks, Deeparnab. Thanks for being here, and please take it away.
Thanks, Akash, and thanks for everyone to coming back again for lecture 2 of this series. So let me begin with a quick recap of the problem that we are going to study and what we sort of saw in last lecture. Okay, so we're going to talk about today Boolean monotonicity testing on the hypercube domain. So there's a function which is defined on the d-dimensional hypercube, and the range of the function is 0, 1. So it's a Boolean function. And it's a good picture to have in mind as a good corresponding picture is if you look at the positions in the hypercube, the points in the hypercube where the function value takes 1, that defines a subset of the hypercube. And equivalently, a Boolean function can be defined as a subset of this hypercube, which I'm going to denote as a green blob. Okay, so that's a Boolean function. And what is the problem? Or what are we going to look at? We're going to look at the question of designing monotonicity testers. And in particular, we'll be talking about non-adaptive one-sided testers. So what are these? So these are randomized algorithms, which tosses some random coins and queries the function at locations q, which is a subset of 0, 1 to the d. Then it obtains the answers, and after that, it will do some computation, and it will either say yes or no. And the one-sidedness says that if the function is monotone, then it must say yes. So it must say yes with probability 1. But if the function is far from monotone, and what does that mean? It means that if the function is at least epsilon, where epsilon is a parameter, that is, I have to change the function in epsilon times 2 to the d points, at least, to make it a monotone function. In that case, the function should actually say no with some decent probability, so probability at least 2/3. So that was the definition of a monotonicity tester, in particular a non-adaptive one-sided tester. So what did we see? We saw that there do exist testers which run for constant epsilon in query complexity logarithmic in the domain size. So in particular, domain size is 0, 1 to the d. So the edge tester, which basically says pick a random edge of this hypercube and test for monotonicity among the endpoints of this edge. If the function is far from monotone, then it succeeds with probability roughly 1 over d. So if we repeat this around d times, you will catch the violation. So again, what is an edge? Edge is a couple of points x and y of the hypercube which differ in exactly one coordinate. So this was the edge tester, and we saw an analysis of this. We saw this succeeds with this above test succeeds with probability at least 2/3 if the function is far, and of course if it is monotone, it never rejects. We saw this, and we also saw that this tester, as in this analysis, is optimal because there exist functions which where the probability of catching a violated edge will be roughly 1 over d. And the canonical example is this anti-dictator, which has 1s on one side and 0s on the other side. So the number of edges is actually roughly epsilon times 2 to the d. And since there are d times 2 to the d edges, the factor is 1 over d. We also saw an example, an idea of how to get beyond this order d, or beat the running time of d. And the idea was, instead of comparing endpoints of an edge of a hypercube, you want to compare points which are far away. So in particular, we talked about this path tester, which goes as follows. You pick a point x at random, and then you sort of walk up the hypercube, which means I flip some zeros of x to 1s to get a point y, and I query these two things. So these are comparable points. If fx is 1 and fy is 0, then I should reject. We also saw that I cannot quite flip a lot more because we can always assume that the caps are satisfying monotonicity conditions. So in particular, any 2 points you query, they should be lying in the middle layers, which means their Hamming weight should be d by 2 plus minus some square root c times square root d. So you cannot really travel more than square root d. You cannot. There is no information obtained when you query pairs which are more than square root d apart. And we sort of saw that for the hypercube, not the hypercube, I'm sorry, for the anti-dictator function like this, we saw sort of a back of the envelope calculation why the answer should be like 1 by root d. So let me give a little more detail about this path tester. And this is what we will analyze today. So the path tester, the amount of thing that you walk, we said should not be, cannot be more than root d. And for this anti-dictator, the longer you walk, the better my chances to catch are. But that is, in general, may not be true. So what this path tester does is the amount that it walks, this parameter tau that you will see, that is also chosen randomly at the various scales. So from 1 to powers of 2, from 1, 2, 4, 8, 16, up to roughly root d, it is going to choose one of these lengths at random. So there are log d such lengths. And then it's going to sample an x and walk t steps to get y. So it'll flip t zeros of x to get y and then test. Okay. Again, why are we choosing this tau at random? That is something we will come to, hopefully, and hopefully I'll be able to impress why this might be needed. But for now, it's basically think of that, how much to walk? Well, I don't know how long to walk, so I'm going to go at all scales and I'll try them at random. This leads to a hit of a log d factor. And for us, for this talk, log d is something which is like small change, but they will always be there. Okay, so this is what we saw, like for this anti-dictator. Actually, for this particular, we should just walk as long as possible. And, the chance of catching a violation is 1 by root d. And roughly the reason is we want to catch the edge that straddles this dimension where the violations occur. And the longer you walk, the more the chance.
There is a question. The question is, which set of zeros will be flipped?
So you flip a set of random zeros. So x will roughly be in the middle layer. So there'll be roughly d by 2 zeros of x. So you're going to pick a subset of tau things at random and flip them. So that's equivalent to sort of walking up randomly up the cube. Thank you. Again, maybe I should have mentioned it. If there is a question, just unmute yourself and ask it. That might be much more efficient.
Sorry, Deeparnab.
Yeah, Jaikumar.
I'm just, so the gaps are always odd in this case, or what? Between the starting point and the ending point? Or always, or most?
Sorry, when you say gap, you mean the distance?
No, meaning the distance. Oh, sorry, distances are 2, 4, etc. Most of the time they are like powers of 2, right? Or
yeah, most of them are powers of 2.
yeah.
Correct.
So if the function was constant on like even layers and odd layers, to be will it sort of somehow escape?
One will catch it.
Sorry?
One will catch it in that case.
Oh, one will catch it, but
yeah,
and that is the 1 over square root d. That's good enough for you.
Oh, the example that you say, that's a constant probability I'll catch it, because there are lots of violating edges in the things which are. So every edge is violating, or every other edge is violating, right? Across the layers. If I understand you correctly, it's like 0, 1, 0, 1, 0, 1, right?
So
yes,
maybe
that's right.
X is also chosen at random.
Yeah. So X is also chosen at random. So sorry, just to understand. So you start from an X and you go directly to Y and you compare the F values there, right?
Correct. So if tau is chosen to
you
be
don't
1,
actually walk and look. Yeah.
Yeah, no. So good. So yeah, important point. So I don't look at any points in the middle. I just directly go to Y. But if I choose tau to be 1, which happens with probability 1 by log d, then it's basically the edge tester, right? Because I'm going to choose an X and a random neighbor. And since if there are lots of edges, then you will catch it. Maybe there's a log d hit.
I see.
Does that make sense?
Okay. So yeah. Okay. Yeah. So even having one number in this range, 1 to square root d, I mean, is good enough for us, because that already gives you 1 over. Okay. Got it. Fine. Okay. Got it.
Good. Yeah, thank you. Yeah, this will be perfect.
So
If you
if,
just
I mean, in particular, if you didn't have that 1 and it was just 2,
Yeah.
4 square root d, then this example would have been awkward. Okay,
Yeah.
got it.
That's a good point. Yeah.
Yeah.
Good. Thank you. So, so this is what we sort of talked about last time, and we ended with this maybe. Oops. We ended with this thought like, okay, fine. This idea of flipping and going from the green zone to the blue zone. The more you walk, the better you'll catch it. That's okay for maybe the anti-dictator. Maybe you see how to fill in the details, but no, not all monotone functions are anti-dictators. And so what do we do in that case? And so this is the part where I sort of mentioned that structural results on how far from monotone functions look like is going to be key for the analysis. So today's talk is, think of it as in maybe 2 parts. The first part is for me to explain what these structural results are. And then tell you, second part is tell you why these things allow us to analyze the path tester. I will personally not go into the proofs. I'll not have time, given my thing from last time. I don't think I'll have time to say anything about the proofs. But Seshadri's talk will actually, basically, the first talk will be about the proofs of, he'll begin with the hypercube and then go to hypergrid domain. So my goal is to tell you what these structural theorems are and tell you why they are useful for the analysis of the path tester. So that's the agenda for today. And in general, I would like to, the theorem that is true is that this tester, if the function is indeed far from monotone, epsilon far from monotone, then the probability that I catch a violation is roughly epsilon squared by root d. And when I say roughly here, this roughly is hiding some polylog d factors in the denominator. And one of the polylogs comes from this this tau, which is that only one out of log d of them might be working. Good. Any questions? Any other questions about what the tester is?
So just to
Sure, Rohit. Yeah.
You're gaining in D but you're losing in epsilon. Is that correct?
As opposed to the edge tester? Yes,
Yeah.
absolutely. Yes, yes. In fact, since you brought it up, Khote Minzer, so this whole talk is going to be about works from a paper of mine with Seshadri, but mostly on a result of Subhash Khote, Dor Minzer, and Shmuel Safra. They actually talk about this relation between epsilon and d, and they have this, if epsilon's exponent is beta and d's exponent is alpha, they actually figure out what the correct, relation between alpha and beta is. So there is, if you are interested, but yeah, you are absolutely right. This one loses in epsilon, but gains in d. And again, I would like you to think for today, epsilon is a constant, like 10% or 1%. So gaining in d is the main thing.
Okay.
Thank you. Other questions? Fantastic. Okay, so let's go into structural results, and we already talked about them a little bit last time. So let's begin. So I'm going to talk about, again, this function. Wherever the function value is 1, you can think of it as a subset of this hypercube. And there is a notion of this boundary of the subset that we talked about. It is basically the edges that are incident on this subset, the hypercube edges that are incident on this subset. So right now we are in the undirected cube. The graph is the hypercube graph is the undirected. And we talked about this notion of the boundary size, or the normalized boundary size, which you call phi a, which is this number of edges by 2 to the d. And what I said is that there is this folklore theorem, which is actually more general than just this statement, is that oh, there's a typo here. This should be phi a. That if the variance of a is large, and the variance, you should think of this as it's balanced. Like, so it's not, the fraction of zeros is also a constant, the fraction of ones is also a constant. If that is true, then this quantity phi of a, not phi plus, but phi of a, is also a constant. So there are lots of edges crossing the boundary. So that's the Poincare statement. And what we showed last time, which implies the edge tester, that if you look at the directed version of this question, so I direct all the edges of the hypercube going from directed from lower Hamming weight to higher Hamming weight. And I only consider the out boundary of this of a set A. So that those are these arrows that are marked in dark here. Then the phi plus of A is the number of directed out edges divided by 2 to the D. Now, clearly, if one is the set of ones is monotone or down closed, there are no edges leaving the set because, by definition. And what the GGLRS or Goldreich et al.'s result was actually sort of the version of Poincare where the variance of A, the number of ones or the balancedness of the function, is replaced by the distance to monotonicity. So the theorem that we actually showed, the proof we saw last time, said that if a function is epsilon far from monotone, then the number of violated edges is actually large. So in particular, this directed out boundary normalized is also at omega epsilon. And this omega is actually, in fact, 1, I think, the constant in front of that. So it was very tight. This has been figured out. So, and I mentioned this last time, that GGLRS can be thought of as a directed isoperimetry theorem. Isoperimetry theorems are precisely these kind of statements which connect how big the boundary of a set looks like to its volume. And here the volume is the number of ones in the undirected world, and the boundary is the edges crossing it. And now GGLRS is a directed isoperimetry statement where the volume is replaced by this distance to monotonicity. Okay, so we're going to have much more nuanced statements and stronger statements than GGLRS in a bit. So let me sort of build to those statements. So first, I want to just think about the boundary as this, this is the bipartite graph of what I'm calling influential edges or edges that have the both endpoints different. So we're going to talk about this bipartite graph. Basically, it's the set of ones here.
So these influential edges are not necessarily violations. Is that correct? In this bipartite graph, I mean.
Yeah, in this one, it's undirected, so they're not violations at all. It's just the edges whose endpoints have 0 and 1. And right now, in the undirected world, the directions are irrelevant in some sense. So I'm just sort of, so whenever there are no arrows, it's undirected.
Good.
What is going to happen is I'm going to tell you a bunch of statements in the undirected world, and I'm going to tell you that rather surprisingly, even in hindsight, things hold on for the directed version. So I'm going to build the undirected world first. So this is just a bipartite graph, and the directed coming to yours. So if you look at the directed world, then it is a directed bipartite graph. But what we really care about for monotonicity is the top half. Okay, so those are the violating edges where I'm going, the edge goes from a 1 to a 0. And the things in the bottom here are really, if you catch such an edge, it does not tell you much for monotonicity. So that's the graph. This is the graph we'll be, for monotonicity testing, we care about. Okay, good. So these edges are the directed influential edges. Okay, coming back to undirected. So we're going to call for any x in the hypercube, we're going to call influence of x. It's also called sensitivity of actually, but in this monotonicity literature, it's been called inf of x. It's basically the number of influential edges incident on x, which is basically the degree of x in this undirected graph G. Okay, so we're going to call that inf of x. And so what is the average inf of x here? So I look at, it's basically the simple calculation. I just look at all the x's and look at their degrees and divide. Now let me point something here. It's a technicality, but I will come to this technicality maybe at the very end. So I will ask you to sort of squint at it. So I'm here looking at only the x's which are green, only the x's where the function value is 1, and I'm counting the influence of the degree. In some sense, not to overcount. Okay, I don't want to count the same edge more than 1, so that's what I'm doing. And yet I'm dividing by 1 by 2 to the d. Okay, I'm not dividing by 1 by the number of greens. And the way to think about it is that influence of x is only defined for the influence of x is defined to be the degree only if it is green, only if the function value is 1, otherwise it is 0. So that's that's the definition to keep in mind. That's it. And so that's why you actually, this is a correct statement if you interpret it this way. So infx is only is a degree only if it is green, otherwise it is 0. And then 1 by 2 to the d is the correct normalization. Okay, and so you get this. And what you get is basically the sum of the degrees is nothing but the number of edges in this bipartite graph. But the number of edges is precisely the edge boundary. So you basically get this phi of A. Okay, so I'm just saying that phi of A is nothing but the expected inf of x. Okay, there's nothing. So to okay,
So
IF.
Deeparnab, just to understand,
Yeah.
this degree is just all neighbors in the hypercube, or only the neighbors obtained by flipping zeros to ones or something like that?
So the degree is in this bipartite graph. So the degree of this vertex, for example, is 2 here. But actually, this vertex could also be this vertex, as in it could also have neighbors below. So its degree is the total number of edges that go to the blue zone in this undirected graph.
So you take the hypercube, color it 0 and 1, and a degree of green vertex is the number of blue neighbors it has.
Absolutely. It is precisely the sensitivity of this x for this Boolean function.
Okay. And whether these neighbors are above or below it is not counted in the degree.
For undirected.
Right.
And we'll be talking about directed influence. At that time, we'll be looking at only the out neighbors, which is coming up.
Oh, thank you.
But I'm just sort of recasting this, and for reasons that will be clear soon. But this phi of A quantity, the number of edges, is nothing but the average influence, or the average sensitivity, as it is called in Boolean function. It's basically, I'm looking at the influence of across of any vertex picked at random. And the only catch, and you can forget about it for the stock, the only catch here is that I am defining influence to be the degree for the green things, for the ones, and 0 for the others, so as not to overcount in some sense. So what Poincare can be restated as is, if variance of a function is epsilon, the function is balanced, then this average sensitivity is also a constant. So that's restating of that. And now we're going to talk about directed influence. And now with the directed influence, we are only caring about the out degree of x in the directed graph, which goes from, top to bottom. And so we are only looking at edges that go from green to blue. And similarly, we can define the average influence, which is going to be called IF plus, so the directed average sensitivity. And now it is precisely the number of edges that go from green to blue, number of violeted edges divided by 2 to the d. And that's precisely the 5 plus A that we had. And so GGLRS can be thought of as, if distance to monotonicity is large, is a constant, then this directed average sensitivity is also a constant. So this is just a recasting of all these things. Okay. So let me begin by saying that this Poincare, now I'm back to the undirected world, the Poincare has slack. Now, the statement, we know that Poincare is actually tight, and the anti-dictator shows this. So if I have an anti-dictator, the volume, the variance is constant, it's half or quarter. And indeed, the number of influential edges is, constant times 2 to the d. So the average influence is also a constant. So in that sense, Poincare is tight. But in some cases, it's extremely slack. Okay, so the example to understand here is this anti-majority. So the function value is 1 if the number of ones in x is less than d by 2. So the bottom half of the hypercube is 1, and the top half in the notion of Hamming weight is 0. So that's the anti-majority. Now, if you think about it, let's figure out what the average sensitivity of this function is. Well, to figure out, let's look at the bipartite graph is basically the middle layer of the points which have edges, which those green fellows have edges outside to the blue fellows. So, and each such fellow here has roughly d by 2 minus 1 maybe, depending on if it's d is even or odd. But these many edges come out. So each of these vertices had degree roughly d. But how many such vertices are there? Well, that's the middle layer of the hypercube. So the fraction of vertices there is like 1 by square root d. So if you multiply 1 by square root d and d, what one gets is that the average sensitivity of this anti-majority is actually roughly root d. The volume is, variance is epsilon, but you know, the Poincare says it's at least epsilon, but it's actually much, much larger. So that's in some functions, it is extremely slack. In other words, if you think about monotonicity testing, the edge tester will do really well in this anti-majority. It will succeed with probability, in fact, 1 over square root d instead of 1 over d. That's because there are lots of violating edges here. So I think the isoperimetric theorems in the undirected world sort of try to capture what more nuanced statement can one make. And the first such thing was done by Margulis by looking at not just the edge boundary, but also considering the vertex boundary. Okay, so what do I mean by that? So this is the bipartite graph, but there are many ones that I have not shown. So there are a lot of interior ones which only have all its neighbors are ones. For example, in the anti-majority in the previous slide, anything which is not in the middle layer, below the middle layers, they're all sort of in the interior. All their neighbors are also green. So if I flip a bit with d by 3 ones, once, then all its neighbors are also green. So Margulis suggested that we should look at the vertex boundary and the edge boundary, the interplay between that. So this is in picture, that is the vertex boundary. So more formally, and I'm going to look at the normalized one. So I'm going to look at the number of x's which are 1, which are green, so that there is at least one influential edge incident on it. And I divide by 2 to the d. That's what going to be my definition of vertex boundary. Or said differently, it's this. I look at a random one and I define, basically I look at if there is any influence at all. Okay, so that's an indicator function of whether there is anything coming out of that vertex. And this quantity is called the vertex boundary, which I'm going to denote as gamma f. So is there any question about this vertex boundary? Is it clear? So the vertex boundary is basically all the green vertices, all the ones that have one edge coming out of it, and I'm still in the undirected world. So again, to sort of put this in context, so if you look at the anti-dictator, every vertex, every one vertex is in fact in the vertex boundary, because every vertex has one edge going to the blue zone. So although the number of edges was low, the expected influence was constant, 1. The expected size of the vertex boundary was large. That was also 1. Okay, and it should be theta 1, maybe it's half or something. On the other hand, in the anti-majority, there were lots of edges. Poincare was slack. So the expected influence was actually root d instead of just constant. But the vertex boundary was really thin. It was like roughly 1 by root d. Now you can see that this is 1 times 1, this root d, and 1 by root d is also 1. And what Margulis said is that this is not actually an accident. So Margulis's theorem is that if you take any function with constant variance, a balanced function, and you look at the edge boundaries and their vertex boundaries, then they satisfy this property, that if the function is balanced, then the product of the edge boundary and vertex boundary is a constant. So the way to interpret this maybe is, so before I interpret this, let me pause and see if everyone is convinced that this statement is a stronger statement than Poincare. So Poincare says that this number if is omega epsilon. Margulis says that the product of the edge and vertex boundary is omega epsilon square. So I want to just pause and see if everyone sees that this implies Poincare. And the reason is this quantity cannot be bigger than this quantity, right? Because this quantity is 1 whenever influence is bigger than or equal to 1, and this quantity is actually computing the influence. So IF is only bigger than gamma F. So if this is bigger than omega epsilon square, then gamma F is bigger than epsilon, which implies IF is bigger than epsilon. So this actually implies Poincare. And the way to interpret this is Poincare says that the vertex edge boundary is ye large, right? It is as big as the variance. But if it is tight, as in the anti-dictator, then there are lots of vertices in the vertex boundary. Contrapositively, if I have a function which is as low as a constant is balanced, but its vertex boundary is small, then it must have lots of edges coming out of it, as in the anti-majority. So that is the way to maybe interpret Margulis's statement. So any questions about this statement? Okay, so again, almost syntactically, we can now think about what happens in the directed hypercube. So again, there was this average directed sensitivity, which is the number of directed edges coming out of it, the directed edge boundary. Now you can define the directed vertex boundary, which basically says how many of these vertices once have some violation incident on it. That's the directed vertex boundary, again, normalized by 2 to the d. And what we proved with Sesh around 10 years ago is that it's the directed analog of Margulis, that if a distance is far from monotone, if the distance from monotonicity is epsilon, then actually the vertex out boundary and the vertex, edge out boundary times the vertex out boundary is epsilon square. Again, what it means is if the number of violated edges looks roughly like epsilon times 2 to the d, where Poincare or GGLRS is tight, then it must be the case that there are lots of vertices that escape, just like the anti-dictator. And why is it going to be useful for the path tester? Again, sort of the same idea that there are many ways to escape this zone. So that's going to be only good. So that's sort of the idea. I'm going to describe this.
So Deeparnab,
This is a statement.
So this dictionary, like the analogy between like Poincare and this directed analog of Poincare, like that you're building up, like even like at the surface of it, like I do not yet see if like there is any intuition why distance is the right replacement for variance in this world. Is there some explanation that you have?
Yeah, so the short answer is no. As in, it has happened. Yeah, it's quite remarkable that the variance can be sort of removed by distance, and you get these theorems. So the short answer is no. I don't know why this is at some qualitative level. What is, if I can say it to you, it is also true that the proofs are so different. So by the way, all the proofs, so the Poincare, Margulis, and the one that will come up in a little bit that I'll say, the proofs in the undirected world are just very simple inductive proofs. You take a dimension, you divide the function into 2 pieces, you inductively prove up, and then you add up the things that are crossing the boundary. They're really maybe 2-3 pages. But that is not true for the directed analog. So that's one thing I'll say. The second thing I'll say, that actually the directed analogs imply the undirected. So these are generalizations. But I think you're asking what is the reason that I can replace variance by distance, and I don't know if I understand that.
Okay. Thank you. That was the question.
Good. Other questions?
So is the implication from directed to undirected easy?
It's not trivial, but it is not very difficult either. So you need to use a little bit combinatorics to get there, but you can. It's something that is not very difficult.
Okay.
Okay. Okay. So let me spend a little bit time before showing you another isoperimetry result. Let me actually show you why, say, the directed Margulis is relevant to analyze the path tester. So I'm going to do this sort of back of the envelope kind of thing. Some things I will be pushing under the rug. Some things I will be less clear about, but you should stop me if this is something is unclear. This is our tester. So what is the tester? We choose distance to walk as a power of 2 in this range 1 to square root d. We sample x. We walk up the hypercube from x, or more concretely, we take tau zeros at random from x and flip them from 0 to 1 to get my y, query fx, fy, and test. So that's okay. So that was my function. And let me sort of mark in yellow the vertex out boundary. So that's the gamma plus f. That's the fraction of vertices which have at least one violating edge incident on them. Okay. So what's the probability that my starting point is going to actually lie in that vertex boundary? Well, that's the fraction which is gamma plus f. And now I know that there is one edge coming out of x that is violating. Okay. So x, so this is where I'm going to sort of use the symmetry of the hypercube. So x, if I escape once, then sorry. So let's call that that special edge that takes x to the violating thing like 13 or something. I'm now flipping tau of these things zeros at random. There are roughly d zeros or d by 2 zeros. So the chance that I pick 13 in this out of these tau things is roughly tau by d. Roughly tau by d. So if the back of the envelope, if you think about it, I want to catch this violation tau by d. I start with x is like gamma. So the back of the envelope idea says, well, maybe the chance that I do escape is roughly tau gamma by d. Okay, and this is sort of mimicking the argument for anti-dictator. In the anti-dictator world, gamma was constant, like half or something. Tau, I walk all the root d distances. So this will become 1 by root d times, root d times 1 by d. So this is roughly 1 by root d. So if gamma is large, this is sort of a back of the envelope reason why I would hope to get something like 1 by root d. Of course, the worry is that I might flip x, this coordinate 13, to get to the blue zone y, but the other coordinates might bring me back into the green zone again. So I might start here. I want to flip this bit. So I look at my collection, and if that 13 is there.
Deeparnab, I mean, say one of the tau steps. But we are not checking after each step, right?
No, we are not. So the way to think about it is you picked a subset tau,
Yes.
subset of tau coordinates.
Yes.
And this special edge special dimension 13 is what takes x to this blue zone. And you are looking at, so it does not matter. So you have these things. It does not matter how you look at the walk. If 13 is there, you might say, let me imagine I took that 13 step first, and the remaining coordinates I'll take the walk later. And I'm just reinterpreting, because only how you get to y matter. How you get to y does not matter, right? You look at if you flipped this bit and then you walked again. Does that make sense? So I want to.
Yeah, there are some number of immediate neighbors of x which are kind of colored zero, not in the green region, right? But then we are actually, our y is far away from x.
Exactly.
Y tau, a distance tau above x. Is that how I should think about it?
Yes. So in fact, yeah. So in fact, I only know that at least one edge is outside x, and I'm calling that, I've not drawn it here. There's some y here, and imagine that bit that I flipped to get to y, the immediate neighbor of x is 13. So the good step, this probability here is saying, what is the chance that one of these tau things is 13? That probability is roughly tau by d. And I'm going to think of it as that I'm going to take that 13 step first, and the remaining tau minus 1, which I have picked, I'm going to start from this vertex here and go. And the worry that I'm trying to say is here that might get me back to the green zone. So
I mean, you
Sure.
called it y, but it is not the same y as the y in the algorithm, right?
no. So yeah, sorry. Yeah, I should have called it z.
So let's say it's x prime. It's x prime.
X prime. Yes.
Yeah.
X prime is blue, and that is great. But I'm not seeing x prime at all. I'm actually walking tau minus 1 steps from x prime, the remaining tau minus 1 things, and that walk might get me back to the ones again. That's a big worry.
Got it. Okay, got it.
Good. So that's why this back and it's important to know that in the anti-dictator it did not happen because the anti-dictator was actually anti-monotone. So if you escaped and got a 0, if x prime was 0, if you go up, you'll still remain 0. But we are not an anti-monotone function. We are just far from monotone function, and it very well could happen. In fact, in this picture cartoon, I might come up to x prime here, and then enter back here, enter back here. So that's a worry. Okay, so to bypass this worry, we need this different notion, and this is a notion that Khote, Minzer, and Safra introduced. So in our paper with Seshadri, we sort of came up with an analysis which was different. This is a much more clear analysis. And it's a notion of persistence of a vertex. Okay. So a vertex X, so this is now any X in my hypercube. We say it is L persistence if I take out, maybe I have a picture, right? So I pick an X and I call it L persistent. L is a parameter. If the following happens, if I look at all the walks up the hypercube of length L, so I'm looking at L zeros of X, flipping them at random, and I look at all possible such points. So X, this vertex X is L persistent if a constant fraction of them do not change the function value. Okay, so more formally, this is what it's saying. So X is L persistent if the probability, the function value of Y is equal to function value of X, where Y is the distribution of Y is given by flipping L zeros of X at random. This happens with at least some constant probability, 1 by 10. Then I call X L persistent. Is this definition clear? So this is going to be important. Yeah.
No,
Okay.
I mean, so you actually count walks, right? And so for suppose you had X had T zeros, then there are T choose L different subsets that you could flip, and those will be the different destination Y that you could obtain. But but you will be multiplying it by T.
No, I'm not multiplying it. No, I'm not. I'm not multiplying. I'm just looking at the Y.
When you say walk, are you counting only the Y's?
No, I am not.
Or ways to get to Y's?
No, we are not counting the number of walks because the number of walks will always be T choose L for all symmetrically, right?
Okay.
Because I am
T choose L. Yeah. Okay.
So it's basically I'm looking at those these zones, these destinations.
Destinations, the same destination, there might be multiple ways to get to, but you are not disregarding that.
I'm disregarding them, but also because they are the same, going to be the same.
They'll probably give the same distribution anyway, right?
Yeah. Good. Okay, good. So this is the notion, and what and this is the part where I'll sort of not go over the proof completely, but what KMS show is that for small L, okay, small by less than square root D. Small root D will also work maybe, but less than square root D or significantly less than square root D. Small, significantly less than square root D, like root D by log D. They prove this, that if I look at a non-persistent vertex, so a non-persistent vertex is most of the walks, 90% of these points that I get to change their coordinate. Well, that fraction cannot be too large. Okay, so let me interpret this. So IF now is the actual total influence of the function, not directed. It's undirected. Okay, so IF by D is the fraction of edges, hypercube edges, which have different function values in its endpoints. And L times IF of D is, you should think of it, the way to think about this number is I'm at X, I'm walking L edges up. The chance of each edge to be influential is roughly IF by D. So the chance of one of these edges to be influential is L times IF by D. So if every edge in this walk was uniformly at random, then indeed this is almost a kosher proof that every edge is with probability IF by D is influential. So the chance that one of these is influential is by union one, at most L times IF by D. But of course, every edge is not uniformly random, but in the middle layers of the hypercube, and this is where the symmetry of the hypercube is used. In the middle layer of the hypercube, when you take an X at random and then you walk, these edges look very close to being uniform. So so this can be proved using combinatorics, but that's the rough idea. The takeaway is, if a function has low influence, if the function does not have too many edges which are sensitive, and by now I'm talking undirected, not directed, then the number of vertices that you expect to be, most vertices, or these many vertices you expect to be L persistent or non-L persistent. So if L is also small, most of the vertices are persistent. Did that make sense? Okay. Now, the second fact that KMS notice, so this is actually a Fourier analysis fact, that any monotone function has total influence at most order square root D. Okay, so this is you can look at, it's a classic fact. And what they notice is that there is a slight converse to it, that if the total influence of any function is much, much bigger than square root D, in fact, when I say much, it's like 10 times square root D, then there must be a lot of violating edges. In fact, there must be omega square root D violating edges. Okay, so if this quantity IF here was bigger than some 10 times square root D, then number of violating edges is also roughly bigger than square root D. And so, in this regime, the edge tester is great. If there are like square root D times 2 to the D violating edges, then just the edge tester, which is tau equal to 1, is going to catch this violation. So we may assume that this quantity IF is actually less than square root D. And so this is the quantity that if I walk, the fraction of non-L persistent vertices is roughly L by square root D. Okay, so that's the thing to take away. So if L is 1, then it basically says that the number of vertices which are at the boundary is at most 1 by square root D.
So Deeparnab, I'm sorry, can you go over this Fourier analysis fact and what you said after that, once more?
Yes. So it's a so there is if I have a monotone function, then using Fourier analysis, you can prove that the average sensitivity of that function is at most order square root D.
That's maximized by the majority, right? That's maximized by
maximized absolutely by the majority.
Okay, right. Yeah.
The same proof, if you stare at it and you say, well, suppose it is not at most 2 times square root D, suppose it is at least 10 times square root D, the same proof will tell you that there must be a lot of terms which are anti-monotone present in it, and they correspond to violating edges. And you will be able to deduce that the number of violating edges is also omega square root D. So if the influence is much bigger than square root D, and much being like a constant factor more than what the monotone function's maximum thing is, then there must be a lot of violating edges.
Mm-hmm.
And so we can assume that this number is at most square root D, and that leads to this.
I see. Okay. Yeah. Thank you.
Okay, so now if I now use that now, so what was the worry? The worry was that X was not persistent. I want it to be sort of persistent. I want to stick. Once I get to violation, I want it to stick. So that says that the tau, so this is the probability that X is in the boundary and not persistent. So it is persistent. Well, the number of vertices that are not persistent is roughly L by root D. L is tau here, or tau minus 1 here. So it's roughly tau by root D. So if I remove them away from my yellow zone, then the possibility that both of these things happen is like roughly gamma minus tau by root D. And so if tau is roughly gamma times root D, this is omega gamma. Now, here is where we are going to use the fact that I'm choosing taus at various scales. I want my success probability will be that tau, which is roughly gamma times square root D. Gamma is the fraction of the vertex boundary, which can be as small as 1 by square root D. Or it can, so this tau in that case will be roughly a constant. But gamma can also be a constant, in which case, like the anti-dictator, in which case tau should be like root D. So I should walk a lot. Since I don't know a priori what it is, that's why the various scales of tau are chosen. But at that scale, that nice scale where tau is roughly gamma times root D, this quantity is roughly omega gamma. So that's the probability that X is both in the boundary and persistent. And now the older thing, the probability that one of the tau steps escapes is roughly tau by D. So now if you multiply both of these things, what you get instead of a gamma by root D, you get, so gamma root D here, the root D cancels the D and you get the root D in the denominator. This gamma is from tau and other gamma is the probability that I catch it. So the gamma comes as a square at the probability of success. Okay, so there's this gamma square by root D. The edge tester succeeds with probability I by D. So now it becomes a little bit of a proof of concept that you can beat D. So you get these two things, and the isoperimetry says that either gamma is large or I is large, or put it differently, I is at least epsilon by epsilon square by gamma. So you get two success probabilities. And then you basically, balance out and say that this is going to be at least d to the 1 by d to the 5/6, poly epsilon by d to the 5/6. So that's sort of why this gamma and i's dance together.
So Deeparnab, once more, can you go back to the previous slide? I just want to slow things down for my understanding. So here, when you argued that probability that X lies in this yellow region, in the vertex out boundary and is tau minus 1 persistent, you compute this probability and then you motivated why you need to consider different scales for tau. Could you go over that argument slowly once more? I'm sorry.
Yes, sure. So this is saying, so this quantity here has two parameters, gamma and tau. If tau is super large, it might be that this becomes negative. So and gives me nothing. So this quantity to be anything of sense, I want this parameter to be roughly this parameter. So in particular, I want tau by root D to be less than gamma by 2, then I get this is at least gamma by 2. So this is what this is saying. So if the tau chosen by the algorithm was in this quantity, then this good event happens. This quantity will be chosen with probability 1 by log D. The tau that satisfies this will be roughly 1 by log D because I'm going at all scales. And that's what I meant by this. Are there other questions?
No, so when you say that tau approximately gamma by root D, you actually mean something like tau approximately gamma by root D over 2, for example.
Yes.
So that the first, that's what.
Absolutely, yeah. So, yeah. And indeed, tau will be a power of 2. So it's, yeah, absolutely. Other questions? Okay, so then I have a question.
I did not catch the first one.
Yeah. So I want to talk about this because it is okay. So I do have. So this was the argument that X is in the vertex boundary and X was persistent. I guess tau minus 1. X was persistent. This is all fine. There is nothing wrong here. But the point is, I don't want X to be persistent. So let's go back. And again, I'm sorry that I'm calling this vertex Y. This should be X prime. This was the X prime that we were talking about. What was the argument? X has at least one blue neighbor X prime, which I'm calling Y here. And I want to know that this coordinate 13 is picked in the tau zones. That is tau by d. But after that, I should not get back to the green zone. So what I don't want x to be tau persistent or whatever tau minus 1 persistent. I want y to be tau minus 1 persistent. I want to say that from x, there is this coordinate 13, which I walk to. And now from y, I look at the other tau minus 1 coordinates. I picked my random tau minus 1 coordinates now. And I want that with constant probability, I still remain 0. So we don't want x to be tau persistent, but we want y to be tau persistent. Is this clear? As in,
Yeah, only then can I catch the violation.
Only then can I catch the violation. And in fact, I'll draw a picture. If the picture was like this, we will be in soup. So imagine that the vertex boundary of my function is large. So this picture does not happen, but imagine that this happened, that the vertex boundary was large, this long yellow line. But all their violations was with only one vertex y. And furthermore, this y was not persistent because y immediately went to the green zone. Then there is no benefit in being picking something here which is with probability gamma, and maybe they are all persistent because they go from 1 to 1. There is no use of this fellows being persistent. I want this person to be persistent. So the picture like this, if the picture was like I have a big out boundary, but they all come and zoom into a small portion of the zeros, I am in soup. This does not help. But if you think about it, even just symmetrically speaking, this should not be true. As in, if the number of boundary of ones is large, the boundary of zeros also should be large. And indeed, that's what actually we prove. So the directed Margulis was a question about directed edge boundary and directed vertex boundary. But in fact, if you look at the stronger version, is not look at the vertex boundary, but the largest matching of violating edges. So for every person in the yellow, every green guy, I have a blue guy, I have a green guy, I have a blue guy. There's a big matching if I look at that. Then in fact, and if I define that to be gamma, then IF times gamma F is omega square for this notion. And now the previous thing holds. Now for this X, the X prime is the matching fellow, and that I'm going to subtract all the non-persistent fellows from that blue matching size. So I might as well assume that X prime was persistent.
So this is even in refinement of Margulis, right?
Yes, this is the refinement of Margulis. And yeah, so let me way over time, but
sorry, one question.
Yes, Harish. Yeah.
Yeah. So you in some previous slide you had written probability that X is yellow and this tau minus 1 persistent in a previous slide, right?
Yeah.
And then here you're writing tau persistent. I didn't catch.
No, this is a typo. In any case, this is what we want is we want X to be yellow, and we want X prime, which is the matching person of X, to be tau minus 1 persistent.
Correct.
Both of those.
Yeah, thanks.
Excellent. Okay, so if you have this matching structure, then actually the back of the envelope calculation is actually almost, I've given you almost all the details, and you get the d to the 5/6 tester. So how do you get root d? So I want to spend a little time telling you this, and maybe the analysis of the tester I might have to skip because of time, but what the whole point is maybe this slide, right? So I want to, we looked at, say that again?
You still have 15 minutes. Like,
oh, it's not till 1 hour? Okay. So you tell me, Akash, you run the show. So there is this edge boundary. We have this vertex boundary. But really, the point I want to make is that this gamma F, it's not differentiating between vertices which has one neighbor out, one blue neighbor, with vertices which has 10 blue neighbors or 100 blue neighbors. It's counting 1 to each. It's just doing this indicator. So what Michel Talleyrand, this is a very nice paper. He basically said, let's look at a more nuanced quantity, and he defines this, and it's a notion of surface area, and I can talk about it maybe after the 15 minutes. But this is the definition. It says instead of looking, so IF looks at every x and counts the number of the degree of x. Look at the square root of the degree of x. Okay, so this is just a, let's call it the Talagrand measure of this function, which go over every green vertex. Now I'm back in the undirected world, and look at the, instead of the degree, which is the number of sensitive neighbors, don't sum up the degree, but sum up the square roots of the degrees and then average. Okay, so he calls it the notion of surface area. And what he proves is this quantity, is this statement, that if my function is balanced, if the variance is constant, then this object is also constant. Now compare this with Poincaré. Poincaré says that the average degree is a constant. And this is saying the average square root of the degree is a constant. So it's a much stronger statement than Poincaré. And in fact, how does it connect to Margulis? It actually implies Margulis. Now, this is maybe a nice exercise to understand. This implies that by just doing Cauchy-Schwarz. So this is a much more refined and stronger statement than Margulis that Talagrand proves in his 1993 paper. And now you can almost guess what is the next thing. Quote Minzer and Safra proved the directed version of it. So again, the directed Talagrand objective is I look at all the green vertices and I look at the out degrees and I take a square root and I average them. This quantity is large if the distance to function monotonicity is large. This takes time to prove. So this is the part that I think Sesh will begin his talk on the hypercube, but much more as in the generalization that we did in our last year or 2 years ago, I forget, is what does this even statement mean in the richer domains like a hypergrid? So and I think we found a more general proof of this, but it's still a much more complicated statement to prove than the undirected world, the Talagrand, which is just, again, can be done by induction. Okay, so let me at least say why this implies the tester, right? So this is the, now, again, I'm going to lie, there will be a big if coming up right now. I want you to roll with it, and I'll talk a bit about the if a little bit after the analysis. So here is the picture. I have ones, I have zeros. This is the violating subgraph, violating bipartite subgraph. That's the tester at this corner. I have this kind of a statement. Okay, so for now, assume, and this is a big if, assume that all the out degrees and in degrees, okay, not just, but all these degrees here in this bipartite graph are the same or roughly the same. And let's call it delta. This is a big if, but right now, let's see if this was true. Why does it imply a square root D tester? Well, if that is true, if the graph is basically regular, then what do I get? I get that the size of O and Z, the number of ones, out boundary of one and in boundary, are roughly the same. And that's roughly that gamma, the vertex boundary, times 2 to the D. Okay, so that's the size of this. And what does this thing say? Well, this thing says that this sum, which is going to give me square root D every time, and how many times do I do it? Gamma times. This quantity is large. So gamma times square root D is roughly epsilon.
Deeparnab, I spaced out, so I did not follow what you're telling us. If the out degrees are same for every single vertex, every single green vertex, what happens?
So if the out degree and in degrees of all these things, so not just the out degree, I want both the degrees to be same. The graph is roughly regular, like between delta and 2 delta. Then the sizes of O and Z are also roughly the same. And the size of O is defined to be gamma. That's the vertex boundary. I'm just calling it gamma if you don't want it. So, and I'm just saying this is, I'm interpreting this statement like here. It's becomes very simple because everything is delta.
Right. Yeah.
So why does it help in the tester? Well, so this is a tester. What's the chance that I pick X here? Well, that's gamma by definition. And I know that if the number of the steps that I take is roughly gamma root D, then the number, or it should be gamma root D by 2, then the fraction of, tau non-persistent thing is roughly gamma by 2, less than gamma by 2. So most of these Z vertices, not O vertices, these Z vertices are persistent. And so what I want is the probability that I pick one of these fellows is gamma. The probability that now I'm taking tau steps, that one of them corresponds to one of these delta edges incident on this is roughly tau delta by D. So there are 3 edges coming out of this. The probability that one of these tau steps goes either here or here or here, I have now delta choices instead of just one choice from the previous thing. I have delta choices. So that multiplies and gives me tau delta by D.
So sorry. So I was able to show that the right set is persistent. That persistence I was able to show. And okay.
Or what I mean is, whichever fellows are not persistent in Z, just remove them and throw them away. I've only removed 1% or whatever, some constant fraction. So most of Z is still there. Most of these edges are still there. So this Z here is going to be non-persistent because is going to be persistent because I've removed the non-persistent fellows. And so if both of these happen, I'll reject. And if you multiply this, you get gamma times tau delta by gamma. And if I put this tau to be gamma root delta, I get gamma square delta by root D. And this gamma square delta, well, that's the square of this thing. So you get epsilon square by root D. And so this is a big typo here. This should be root D. So I get that the probability
looks like we lost your voice. At least I can't hear you.
Hello, can you hear me?
Can anybody else confirm? Can you hear Deeparnab?
Yeah, I can hear him.
Okay, then please continue.
Okay, so this is a big typo. This should be, of course, root D. And that sort of finishes the proof. And I just want to compare with the previous, like the what just Margulis gives. And you will see that the big thing is that this tau by D is replaced by tau delta by D. And that's what I want. So the gamma, the vertex boundary is not capturing this fact that vertices can have one neighbor or 2 neighbors or 100 neighbors or almost square root D neighbors or D neighbors. It's not capturing that fact. Talleyrand's inequality captures that fact. It's a much more nuanced version. And that's why it gives us this correct answer, which is epsilon square by square root D. But of course, this is a big if, right? Why these degrees, why should they be all delta? They can be, as I just said, on various ranges, 1, 2, 4, 8. So what KMS do, quote Minzer-Safra do, is they say, well, look, I don't need all of O and Z to be well behaved. I just need a subgraph of this bipartite graph to have these features that they're roughly regular in both sides. And this delta and gamma is any parameter, but I just need that gamma times root delta to be large. So they do prove that, but to prove this, they need a much stronger, or what they call a robust version of this inequality. So just this inequality here, this directed Talleyrand, is not enough. What they want is a robust version. And the robust version, I'll not mention much, but Sesh will build on it, or at least tell you what the robust version is. But I'll tell you where the robust version is coming. Now I'm going to bring your attention back to this x equal to 1, right? Which says I'm counting this influence only when the thing is green, but if it is blue, I'm not counting it. That was the meaning of this. But in the case of when there was no square root, things were sort of fine because I'm just counting the edges, either this side or that side. The total number is number of edges. But when I have a square root, the square root is trying to measure how the distribution is varied across the green and blue things. And if I just look at the green things, it only is telling the distribution over the green things. So what Subhash, quote Minzer-Safra, prove is that if you change this, if you say, okay, some edges are counted by green vertices and some edges are counted by blue vertices, and the influence of a x is the number, if they're blue, it's a number of blue edges incident on it, and if they're green, it's a number of green edges incident on it. So and who is picking this coloring? The adversary is picking this coloring. No matter what coloring you pick, this quantity is going to be large. So this is what is called the colorful version or the robust version. And why is it useful? It's useful to actually remove this if and get a subgraph by a peeling argument. So that is, again, it's very fast. But what I wanted to say is that there is much stronger statement that is needed to be proved. And I say this because when we go to hypergrids, a version of this statement is less painful to prove than the version with this robust version. The robust version leads to a lot more intricacies. And what is sort of open at some level is there like a simpler proof of these things? So currently the proof in KMS, the Court-Minzer-Safra paper for this statement is actually a case analysis. We shed some light on the case analysis a little bit. There is some connection to majorization of functions, etc. But still, it's a lot of elbow grease. So unlike the undirected world where it is really 2 pages of induction. So that's one meta open question. Understanding this, like this statement is so pretty. I don't know, maybe it should have a pretty proof. So let me end. Let me summarize what we saw. We saw a Boolean monotonicity testing, the path tester, which is a natural tester, and hopefully I gave you enough intuition of why the square root d by epsilon square arises. But more importantly, I've sort of showed this beautiful isoperimetry theorems of Margulis and then Talleyrand, and that the directed versions exist. And the question that Akash asked, why can the variance be replaced by the distance, at some level is still a mystery. So I don't know the reason. Coming up, hello, can you hear me? Okay, what's coming up?
Yeah.
So the next week, Hadley is going to talk about the hypergrid domain. And basically what we have realized, it's a much richer domain than the hypercube. At first glance, it might feel like, it's maybe just an epsilon increment to the hypercube, but we believe it's not so. It's a much richer domain, and we'll see, Hadley will show some examples, some conjectures where, restricting to some hypercube sort of fails. So we need generalizations of these isoperimetry results, and that's what we were able to do last year. So this is what Hadley and Sesh will talk about. I think Sesh will talk about the generalizations. But let me at least end with, even for the Boolean hypercube, some questions, or maybe the first question is just for the Boolean hypercube and Boolean function of Boolean hypercube. We've been only looking at non-adaptive testers. All the queries are made up front. What can you do? We don't quite understand what the power of adaptivity is. Can adaptive algorithms be more powerful? So in a beautiful paper, Blaise and Belovs and Blaise proved that there is a d to the 1/4 lower bound for adaptive testers, and then Chain, Weingarten, and Shi improved that lower bound to cube root of d. So there's a gap between cube root of d and square root of d. The Chen et al. Paper actually prove a lower bound, a family of functions that are hard, and they in fact give an algorithm which gets cube root of d for those functions. Is there something to get there to improve square root d for using adaptivity? That's a big open question. I don't know the answer. I don't have a guess even. And much more generally, connecting back to my first talk, for general posets, nothing is known. But can we get other such results for other posets which have such symmetries? Like maybe Hypercube was maybe one of the toy versions, maybe other posets coming from Cayley graphs, etc. These have been completely unexplored. And maybe there are other isoperimetry theorems to be discovered there. Okay, so with that, I'll end. Thank you for your patience. And I'm happy to take questions.
Questions, guys?
Yeah, so I have a question. So so you can hear me, right? Yeah.
Yeah, I can hear you. Yeah.
Yeah. Okay. So what about two-sided error testers here?
Can you repeat the question? What about?
So two-sided error tester, like.
Yes. So two-sided error tester does not really buy much if you are non-adaptive. So there is this Chain, Weingarten, Shi, this paper which proves this lower bound has a cleaner proof which says that if you are two-sided but non-adaptive, you cannot do better than square root d. Like maybe you can do better than like up to log factors.
But what about both, like adaptive and two-sided?
Yeah, sure. As in you are allowed to be two-sided. It will be fantastic to beat square root d.
I see. Okay, thanks.
More questions or? Yeah, I guess perhaps that is all. So thank you very much, Deeparnab. Thanks for the beautiful talk.
Yeah,
and
thank you, Akash. Yeah,
we'll upload it soon and we'll let you know. Yeah, thank you.
sure. Okay. Thank you. Thank you, everyone. Bye-bye.
Thank you. Bye.